Basic operations. Our mathematical journey often begins with four fundamental operations: addition, subtraction, multiplication, and division. Let's start with addition. It's a remarkably well-behaved operation, being both commutative and associative. It also possesses a unique identity element, the number 0. Add 0 to any number and that number remains unchanged. Now let's consider subtraction, which acts as addition's fundamental inverse operation. This means it effectively undoes addition. If you add two numbers together, you can perfectly revert this by subtracting one of those numbers from the sum, leaving you with the other. Here's a key point. Because addition is commutative, subtraction offers a symmetrical capability. The same inverse operation allows you to isolate either of the original components.
Following addition, we encounter multiplication, an iterated version of addition. When we multiply a number by 3, for example, it essentially means adding that number to itself 3 times. Like addition, it is both commutative and associative over the reals, and even complex numbers. It also distributes over addition. Multiplication also has an identity element, which this time it's the number 1. Any value multiplied by 1 remains unchanged. It also has an absorbing element, the number 0. Any value multiplied by 0 becomes 0, absorbing the original value. Since multiplication can be understood as iterated addition, we can define it using induction. We need a base case and an inductive step. Our base case will show the behavior of our identity element, the number 1. The inductive step will show what happens to any number larger than 1 in terms of the previous number. For instance, to multiply by 4, you first need to understand how to multiply by 3, and that in turn depends on knowing how to multiply by 2, and so on until you reach our foundational base case. While this recursive framework perfectly describes multiplication for positive integers, it's just a conceptual skeleton. The operation itself extends beyond integers to encompass all real and even complex numbers, where the idea of repeated addition loses its meaning.
Just as subtraction undoes addition, division serves as multiplication's inverse operation. If you multiply two numbers together, you can perfectly revert this by dividing the product by one of those numbers, leaving you with the other. However, there's a vital exception. Since 0 is multiplication's absorbing element, division by 0 is undefined in common number systems like the real or complex numbers. There's no number that, when multiplied by 0, yields a non-zero result, making division by 0 an impossible operation.
Exponentiation. It is the iterated version of multiplication. Taking something to the third power means multiplying it by itself 3 times. Because these iterated operations are defined in terms of simpler ones, the more iterations you make, the larger the numbers you get using small values. Since it's defined in terms of multiplication, we can also use this recursive definition, including the base case and the inductive step. Just like multiplication, it can be generalized to non-integers, and this is usually done by the Taylor series definition of the exponential function. Unlike the previous operations, exponentiation is not commutative, nor associative. However, it can distribute over multiplication. Because it is not commutative, it doesn't have a full identity element, but only a right identity element equal to 1. The number 0 behaves almost like an absorbing element, but it turns most numbers to 1 rather than itself. Since it lost commutativity, an interesting thing that ends up happening at this level is that there are two different inverse operations. The first operation, the nth root, such as the square root, can be used to cancel the exponent. The second operation, the logarithm, can be used to cancel the base. These operations can also be considered inverses of each other. There are 6 possible cancellation rules using these 3 operations, and some have even proposed alternate notations to make them easier to visualize. Tetration. So far, we have seen a chain of operations being defined as iterations of simpler operations. These are called hyperoperations, and tetration is the 4th level. We don't hear about this one a lot in the real world because it's not as useful as the previous ones. Although its notation is not standardized, it is most commonly represented similarly to exponentiation, but with the height or hyperexponent on the left side, or by 2 upward pointing arrows instead of only 1, like some representations of exponentiation. Some interesting arithmetical properties stop working after exponentiation, so tetration remains not commutative and not associative, and this time it doesn't distribute over the previous hyperoperation. It can also be defined using recursion in terms of exponentiation, just like how we have seen previously. Its most popular property is how fast it grows, even faster than exponentiation. It also has two inverse operations, the superroot and the superlogarithm. An interesting fact of tetration is that it's possible for operations with infinity to converge to finite values. An infinite power tower of the square root of 2, for example, or the square root of 2 tetrated to infinity results in 2. All bases that converge for infinite tetration are found inside a region in the complex plane called shell-thrown region. For real basis, they are bounded by e to the power of negative e and e to the power of 1 over e. But what happens at heights that are less than 1? Tetration of 0 is also 1, just like exponentiation. Tetration of negative 1 is 0, and tetration for other negative integers are undefined, kind of like the logarithm of 0. For non-integers, things can get a lot more complicated. There isn't a single agreed-upon definition for tetration of rational or real values. However, it has been proven that there is only one possible complex extension of tetration that holds these desirable properties. To grasp its workings, you'll need a strong foundation in very advanced mathematical topics, including complex analysis, functional equations, iteration theory, and dynamical systems. But at least this operation gives us some pretty cool graphs. Pentation. So if tetration is already pretty unknown, not very useful, and grows very fast, pentation is all of that, but so much more. If 2 to the power of 3 is 8, and 2 tetrated to 3 is 16, 2 pentated to 3 is 65,536. But to be honest, hyperoperations after this level behave pretty much the same. They all iterate over the previous hyperoperation. Identity element is always 1. They are never commutative, nor associative, nor distribute over the previous operation anymore, and they all have two inverse operations. The notation for these operations is not standardized, so there are lots of ways to represent the nth hyperoperation. Defining each operation for positive integers is straightforward using recursion, but generalization for non-integer values becomes even more convoluted, since you need to define them for all simpler hyperoperations than the one you're trying to calculate. They are useful for generating astronomically large numbers pretty quickly, but they don't offer us any new interesting properties. Infinite hyperoperations. We already know we can keep generating hyperoperations at higher and higher levels, but what happens at infinity? The limit hyperoperation as the level approaches infinity is called circulation. It keeps some properties that we have already seen repeatedly before. 1 is the right identity element. 1 circulated to anything is 1. Circulation of 0 is 1. 2 circulated to 2 equals 4. Anything larger than 2 diverges. It is hypothesized that numbers between 1 and 2 result in themselves when circulated to infinity. And that's pretty much it. There's nothing much you can do with it since most things diverge to infinity. That's kind of boring, to be honest. But there is another way we can approach defining an infinite hyperoperation. Using transfinite ordinals, things get a little bit more interesting.
A hyperoperation of level omega of A and B can be defined as the hyperoperation of level B of A and A. This is similar to the definition seen in the fast-growing hierarchy, a common concept in googology. While this doesn't look that large, a hyperoperation of level omega plus 1 can be defined as an iteration of omegation B times. This grows pretty quickly, and that's arguably more interesting than diverging to infinity most of the time. Things can get pretty wild after that, but let's just leave all that to the googologists.
Zeration. Instead of going forward, what happens if we go backwards? What is the 0th hyperoperation, and what would negative hyperoperations even look like?
If we take a look at the foundations of mathematics, addition is defined in terms of an operation known as succession, or the successor function. It is defined for natural numbers, and it simply means the next number, or that number plus 1. We can easily define addition as iterated succession. But is this truly the hyperoperation at level 0? First of all, it's not even a binary operation. It only receives one value. This also means there can't be any identity element. Some have proposed alternate ways of defining zeration, like these ones, but all of them have some flaws. We can try to keep some interesting properties, but we can't have all of them. One of the main problems is that these two expressions are always true for every hyperoperation so far, but they can't both be true for zeration, as it leads to a contradiction. So we end up having to give up some properties over others. The true definition of zeration ends up more as a matter of choice than mathematical rigor, which is why its existence is considered somewhat controversial. Generally speaking, this definition is the one more commonly used. An interesting consequence of this definition is that negative hyperoperations end up exactly the same every time, so there's nothing new below zeration in this interpretation.
Fractional hyperoperations. We already tried generalizing hyperoperations to less than 1 levels, which didn't go very well. But what happens if we try to generalizing it to fractional values? If 2 plus 3 is 5 and 2 times 3 is 6, what's the result of the operation right in the middle of these two? Can we define hyperoperations at any real number level? What about complex numbers? A possible approach to this in-between operation uses the arithmetic geometric mean. This is the limit value of alternately applying the arithmetic and geometric mean multiple times, which always converges. If the mean of the addition level is the arithmetic mean, and for multiplication it is the geometric mean, the arithmetic geometric mean should point to a new operation at its own level, right between addition and multiplication. This operation has been called sesquation. Here is one possible approach to define it. 2 being operated with 2 and resulting in 4 is true for every positive integer level, and we can choose to keep it always true even for intermediate values. If that is the case, the mean, at the level of some operation, between 4 and the identity element will always be equal to 2. The same goes for sesquation, so its identity element can be found by this formula, where AGMO is the inverse operation of the arithmetic geometric mean. This number is approximately equal to 0.7. Finally, sesquation can be defined like this in terms of this new identity element, the arithmetic geometric mean, and its inverse. Since this mean is also commutative, this operation keeps commutativity, but not associativity. We can generalize this to any dyadic rational number between 1 and 2 by interpolating hyperoperational means. For numbers larger than 2, we can simply define it as the iteration of that level minus 1 until we reach the defined interval. For reals that are not dyadic rationals, we can approximate the result by taking the limit. This is the approximate result of 2 sesquated to 3, and this is a graph comparing the behavior of operations like addition and multiplication with fractional ones. This, however, does not seem like a perfect way to define fractional hyperoperations. The result values don't always change smoothly, not even the identity elements. We also don't have a clear picture of what a halvation would look like. It doesn't seem like it's simple to generalize hyperoperations for any level. Maybe there is a better approach out there.
Lower hyperoperations. Let's take a look at tetration once more. We know that it is iteration of exponentiation, but what does this mean exactly? How to interpret this tower of exponents? In our world, this notation refers to this interpretation. We apply exponentiation starting from the top to the bottom, but it could pretty much happen the other way around. It is simply not the usual way of iterating exponents. If we start from the bottom up, the result will be different, since exponentiation is not associative. This could be considered a brand new operation called lower tetration, or weak tetration, or left tetration, because we do the calculations starting from the left or lower part, and the results are usually much smaller. It can be defined recursively in a slightly different way, just by rearranging the terms in the inductive step expression.
It can also be generalized for higher levels such as lower pentation, lower hexation, and so on. If we take a closer look at the definition of lower tetration for natural heights, applying properties of exponents, we can find this closed form. That's right, lower tetration can be defined entirely using exponentiation. This can easily be generalized to negative, real, or even complex numbers without all the trouble we find with standard tetration. However, as the name suggests, lower tetration grows slower than normal tetration. Lower hyperoperations tend to be way slower than standard ones, so they're often overlooked for not introducing any new behaviors. Their notation is also not standardized. Mixed hyperoperations. Because exponentiation isn't commutative, we can technically define two different kinds of tetration based on the way we choose to evaluate iterated expressions. This also happens at the tetration level, wielding two kinds of pentation, and so on for each level. However, nothing stops us from defining the left pentation of right tetration and the right pentation of left tetration. Lower hyperoperations don't just give us an alternate hyperoperation hierarchy, but allows us to define a whole binary tree of new operations. These are called mixed hyperoperations and grow exponentially in number, doubling the amount at each level. All of these lose commutativity, associativity, distributivity, and have two inverse operations each. The notation is even less standardized since these hyperoperations don't receive a lot of attention. Balanced hyperoperations. What if there was some operation between standard ones and lower ones? Balanced tetration is defined as a middle ground between the two. It still resembles iterated exponentiation, however the parentheses aren't chosen from top to bottom or from the bottom up. They're balanced like this. It's a whole new generalization of iterated operations, and it's completely valid since all of these expressions mean the same thing in the context of simpler hyperoperations. But the choice of which is the correct way to place parentheses is kind of arbitrary. Unfortunately, this operation is only easily defined for powers of q. For other numbers like 3, the process can involve complicated function iterations like we have seen for standard tetration. By this logic, there are multiple ways to define alternate hyperoperation hierarchies based on the way you choose to place parentheses. But the more arbitrary they look, the harder it is to generalize to non-positive integers or even to all positive integers in some cases.
Commutative hyperoperations. It seems that in a lot of ways, trying to extend hyperoperations to non-positive integer cases result in lots of complicated and convoluted results. And the more we look into higher levels, the more chaotic they seem to get. That's probably why some of the results presented here are not always universally accepted. It looks like there is no true extended pattern behind all of this. We are trying to just force things into working out, and we end up needing to hold on to arbitrary choices sometimes. But in the end, things always end up losing properties and becoming less intuitive and useful as we increase in complexity.
Maybe there is no insight to get from extending hyperoperations, but let's take a look at our main hyperoperation sequence again. It seems that everything starts falling apart after exponentiation. It's where commutativity and associativity stop working. It's where we start needing two inverse operations all of a sudden. It's after this level that hyperoperations start branching indefinitely, distributivity stops working, and extensions stop being universally accepted. Let's take a look at right identity elements. It seems that addition is the weird one here, and maybe that's why we can't have a nice definition for zeration. But what if exponentiation is actually the weird one here? What if we're supposed to change the identity element at each level? That's how multiplication kept its commutativity and associativity. If we define an alternate multiplication where the identity element is 0, it suddenly stops having these properties. Here is the recursive definition of multiplication and exponentiation. As we know it, we basically just swap these operations to higher ones in the hierarchy. But what would happen if we did the same thing here, swapping subtraction with division? Dividing by 1 here won't make any difference. Since 1 is the identity element of both multiplication and exponentiation, we need a new identity element here. Let's choose e. This right here is a completely new operation that iterates over multiplication, but in a different way. And even better, it's commutative, associative, and even distributes over multiplication. Here, however, the second element doesn't mean the amount of terms iterated with multiplication. The number of terms is calculated by the amount of times you can divide this number by e to reach the identity element of the previous operation, as opposed to how many times you can subtract 1 to reach the previous identity element, which is what happens in multiplication. This is actually the natural logarithm of the second element. Because of that, we can define this new commutative exponentiation in this closed form, which works for negatives, real, or even complex numbers. Because this operation is commutative, it will have only one inverse operation as opposed to exponentiation. We can apply that new operation generating process multiple times and define operations such as commutative tetration, commutative pentation, and so on. Notice how each identity element needs to be e to the power of the last identity for it to work. The absorbing elements of each operation are also always the identity elements of the previous operations. All of these preserve the same structure, so we can define isomorphisms between them given the right conditions. Addition of real numbers is isomorphic to multiplication of positive real numbers. The way to translate between the two is to apply an exponential function which turns addition into multiplication. This actually happens at every level, so exponentiation is still useful in this world to transform hyperoperations into higher ones. In general, you can start with addition at the first level, which is a plus b. To go to the next level, you take the exponential of the whole thing and map each element to their logarithms.
This way, you can define iteratively every commutative hyperoperation at positive integer levels, and they are automatically defined for any number system, such as complex numbers, if you know how to do exponentiation and take logarithms with them.
You don't need to use e as the identity element of commutative exponentiation. A problem with bases like e is that identity elements explode in size as well as absorbing elements, so it gets pretty hard to do simple calculations on small numbers. You can change it to other bases, and that will result in alternate hierarchies. If we use the square root of 2, for example, the identity element will never end up larger than 2, and we will find the interesting property that preserves this formula. 2 being operated with 2 results in 4 at every level. As you might have guessed, we don't have a standardized notation, but I found this one I really like. It not only shows the level of the hyperoperation, but also the base, such as e or square root of 2, like we have just seen. After seeing all of these patterns, I think to myself that maybe exponentiation wasn't supposed to be the next step after multiplication after all. Even if it is not present anymore, since it is not commutative nor associative, at least it's still lurking there as the isomorphism that connects them all. Generalized hyperoperations. Now that we have a much cleaner pattern of hyperoperations, can we generalize them to negatives, reals, or even complex values? Firstly, if we want hyperoperations at 0 or negative levels, we can do the reverse process we found earlier. Instead of mapping elements to their logarithms and taking the exponential of the whole thing, map elements to their exponentials and take the logarithm of the whole thing. This can be done for any value less than 1 with no problems. Let's take a look at the hyperoperation at 0 level. This is called commutative zeration or pre-addition, and a much more elegant definition than the one we tried defining before. If we use base 2, the commutative zeration of a number twice equals their successor. It kind of resembles some definitions we saw earlier. For different numbers, we have more intricate results, but this allows us to define an inverse operation easily, unlike previous definitions of zeration. If we take an infinite base, on the other hand, or in rigorous terms, take the limit as the base goes to infinity, this operation becomes the same as the max operation, which simply means taking the maximum value between the two. Interestingly, addition distributes over the max operation, and the relationship between the two is studied in tropical geometry. But what is the identity element of this operation? It should be the absorbing element of addition. Negative infinity could be our best guess here since it fits perfectly. The absorbing element of pre-addition, however, would be trickier to define.
Now, taking a step back, what about non-integer levels? We have closed forms for each integer value. Is it possible to find a generalization so that we can just plug in a value and get the corresponding operation at that level? Here comes the plot twist. If we want to generalize commutative hyperoperations to non-integer values, we need to use tetration, standard top-to-bottom right tetration. It turns out it wasn't a completely useless operation after all. Since we end up with cowers of exponentiation after achieving higher and higher levels, it's possible to generalize this process using this formula. These terms apply logarithms multiple times, this term applies exponentials multiple times, and we use x minus 1 to make sure addition remains at level 1. It automatically works for the negatives, switching between taking exponentials and taking logarithms. And the best part?
If you have a decent definition for tetration for real or complex values, you can automatically define what the hyperoperation of level pi looks like, or at level I. You can even plug in quaternions or other hypercomplex numbers if you are feeling adventurous. The relationship with tetration becomes even clearer when we look at identity elements. Maybe this is the most elegant generalization of hyperoperations we can achieve.
Parallel hyperoperations. Here is a bonus. These ones don't actually exist. I kind of made them up. But hear me out. Parallel addition is an operation that actually exists, and its name comes from parallel circuits in electrical engineering. As some of you might know, the equivalent resistance of some resistors in series is simply the sum of each individual resistance. But the equivalent resistance of resistors in parallel is a little more complicated to calculate. But we can define it as if it were a whole new operation, such that the equivalent resistance is the parallel sum of each individual resistance. This operation is not random. It has some quite interesting properties. Let's take a look. Parallel addition is both commutative and associative. If 0 is the identity element in addition, in parallel addition, 0 is actually the absorbing element. The closer to an identity element we could find for parallel addition would be infinity, which, interestingly enough, could be seen as addition's absorbing element. It's interesting how these elements switched from one operation to another. You can understand them even better by noticing the analogy between electrical circuits if you are familiar with these. Here is a more geometric visualization of this operation. The heights of the blue dots represents the operands, while the height of the red one represents the parallel sum. If addition of two positive numbers results in an even larger number, here the number is always smaller. And here's the best part. Adding two equal numbers result in the original number times 2. However, the parallel addition of two equal numbers is actually the original number divided by 2. The same happens with 3, 4, or any other number. Do you know what this means?
Dividing by a number b means applying parallel addition b times.
Division is nothing less than the iterated version of parallel addition. Despite its name coming from electrical circuits, it kind of really looks like a parallel version of addition. There are also some applications of this operation in optics, mechanics, and even statistics. But what about the rest of the parallel operations? Well, parallel subtraction could easily be defined this way. It is the inverse operation of parallel addition, and not much different. However, if we take this definition and change each operation to its next in the commutative hyperoperation hierarchy, including the identity elements, we reach a new operation that I will call parallel multiplication. It has nothing to do with parallel resistors, but it is kind of an alternate version of multiplication, in a sense that instead of it resulting in exponentiation when iterated, it results in taking the root of a number. Applying parallel multiplication to the same number twice results in a square root, while doing it 3 times results in a cubic root, and so on. In the same way as addition, its identity and absorbing elements flip.
1 is the absorbing element of this operation, while 0 is the identity element.
We can also easily define parallel division, its inverse operation. After manipulating this expression a little bit, we can find these other interesting closed forms. This last one is very enlightening because it suggests a relationship between not only parallel addition, but also with commutative hyperoperations. If we apply the commutative hyperoperation iteration on parallel addition, we get parallel multiplication. Not only that, but this process can generate an infinite amount of new parallel operations. Unfortunately, the iteration relationship stops working after parallel multiplication, so I'm not sure what's the relationship between the two hierarchies. Maybe there's an alternate parallel hierarchy where that could be the case. I don't know.
But wait a second, does it still make sense to call any of these operations? Aren't they all just functions based on operations that already exist? What about mathematical means? Could they be considered hyperoperations as well? They can be binary, they can have inverses, some of them are commutative, they can make their own hierarchies. Maybe there is no true definition for what a hyperoperation should be, but at least we saw some pretty cool stuff.